All right. Good evening, everyone. Welcome to our 12th meeting of Math 261. As a reminder, 4.4 and 4.5, I had them marked due as the 11th. I never set those due dates up in my math lab. I kept having issues off and on for some reason. I think I gave you till the 14th. I can check that really quickly. It's not really a big deal. Just give you a couple extra days. Yeah. 14th. Okay. So that's that. Then we'd said test 3 was going to cover 4.1, 4.2, 4.4, and 4.5. So we're still covering 4.6. It's not just going to be in that test. It's kind of there's already a decent amount of material in those 4 sections to call a test, believe it or not. It's going to be 18 questions. You are allowed a calculator, but of course, show all work. I will make that work submission available in Canvas right after class. I have the dates as the 12th through the 14th, but in order to demonstrate what it'll look like initially for the Respondus lockdown browser, I actually have it available today. So if you are feeling really up to it after class, you can go ahead and take test 3 tonight if you really want to, but I imagine no one's going to do that. So you have today, tomorrow, and then Wednesday and Thursday. So Thursday the 14th is your last day to take test 3. 18 questions, 2 hours, no notes, no books, but a calculator is allowed for this one. But remember, you do have to show all your work and submit it in Canvas. This will require a webcam setup. I'm actually not sure about the cell phone camera setup. I never saw that anywhere, but if you know how to set that up, then you can go for it. I spent a decent amount of time working on this, and I never saw a cell phone option available, and you can't use my math lab with your cell phone. So I think you just need to have a computer with a webcam. So I'm going to black that out, take it out, delete it, whatever you want to say. But you do have to have a webcam. So I have instructions here on, it's actually pretty simple. You're going to go to my math lab to take the test. You're going to go to where it says test 3. You click test 3. And then it'll open up another browser. And at the very bottom, there will be an option to download the lockdown browser. And you have to do so. So you click download Pearson lockdown browser after you click test 3. And then once that's finished downloading, if you're in Chrome, the files download to the bottom left. Other web browsers, it might be a different location, but you'll have to open that file and go through it's like 6, 7, or 8 steps. They're pretty simple to set it up. It's basically just a license to use, click the agreement, and then move on. And then it'll make sure your webcam has access, that it can record audio. It'll take a little 5-second clip. You can check it to make sure everything looks good. You'll have to move. If you're using a laptop, you'll have to move your screen up and down a little bit just to kind of so they can see the full room. It'll do a facial recognition thing. Again, it is pretty easy. After you do that, after you go through all the steps, the test should open up normally with the lockdown browser. But if not, you can just go back to test 3 and open it that way. So if you go to my math lab, here's your test 3 due on the 14th. You can't just click start test unless you already have the lockdown browser downloaded. So most of us will be clicking right here to download Pearson lockdown browser. It'll take a minute to download, and I'm not going to show all the steps, but at least show the initial ones. And hopefully it'll let me do that since I've already gone through this process on my laptop. So I clicked it to open the installation. And it did tell me it had to close Zoom when I was doing this originally. So that's why I'm kind of scared to go through this completely. But do you want to allow this to make changes? You click yes, of course. It'll prepare a setup. Like I said, if it tells me I have to close Zoom, I am not going to do that. So reinstall, that'll be for me. This wouldn't be an option for you unless you already have it. Click next. And yeah, I'm going to stop here because this took me like 5, 6, 7 minutes, something like that. Hopefully bad things don't happen with that. Oh boy. I chose poorly. Yes. Okay. But after that, like I said, it'll just be the 6 to 8 steps. Very, very simple to go through. And then after that, you can actually take the test. If you have any issues, you can shoot me an email. I'll try to get back to you as soon as possible, but I don't think there should be any issues. I'd already said if you don't have a webcam to email me, nobody emailed me, so hopefully that's cool with everybody. But yeah, so this really shouldn't look any different. When you're taking your test, when I pulled it up, I did not see my actual webcam screen. I'm sorry, my webcam video on the screen, but it does say in like the top right area, webcam is live. So make sure you're not covering up the video camera with a piece of paper. Make sure it is getting the recording of you and that the video is on you and of the test you're taking. Make sure to go to Canvas to submit your work. Again, I will have that live later this evening. I don't imagine anyone is taking the test until tomorrow, so that shouldn't be an issue. All right. Besides that, the two sections that we will cover and finish tonight are going to be 4.6 and 5.3, going a little bit out of order. I know it feels like, but that's not the first time in this course. So those will be due in a week on the 18th. So let's go ahead and get into that. Give me a second to set up our videos. Okay. All right, so we're going to pick up where we left off with that UV substitution, that integration by parts. So that integral of v du equals uv minus v du. And we had already done up to c, so we're going to do a d and an e, and then we're going to show how to do this as a definite integral. All right, here we go. All right, so not a great path aside. Let's work on the ones that are. Let's do some more. I like lots of practice with this stuff. So let's do about 2 more like this, and then we'll get to one with endpoints, with upper and lower bounds, an area, if you will. So the integral of x plus 1 over e to the x dx. So if you tried the regular old substitution, one student might say, let u be e to the x, and then when you solve for its differential dx, it's definitely not going to cancel the x plus 1. Another student might say, well, just let u be the exponent. And if u is x, its derivative is 1, and it won't cancel this x plus 1 when you go through and plug in the differential. Substitution fails miserably on this problem. Parts is the way to go. So we say, let u be the simpler part. What do you think simpler, x plus 1 or e to the x? I think x plus 1 is simpler. Polynomials are simpler than anything else. Exponentials, radicals, rationals, etc. When you take its derivative, the derivative of x is 1, the derivative of 1 is nothing. When you solve for du, I gotta sneeze again. I got it that time, muted in time. All right, multiply both sides by dx, you get du equals dx. Again, it's kind of funny because substitution technique, you solve for dx, integration by parts technique, you solve for du. These are both solved for the same thing. That's because of the very simple derivative. This can happen. Does it happen a lot? No. Does it happen frequently? Actually, yes. Maybe 20% of the time, 25% of the time. So there's the u branch. Now let's say let dv be the rest, which the e to the x is in the bottom. Be careful there. So dv is actually dx over e to the x. And then when you go to integrate it, oh, that looks terrible. That looks like ex, e to the x. There you go. So that'd be the integral of dx over e to the x, which it's just going to be better to write this as the integral of dv equals the integral of e to the negative x dx. We don't know how to integrate when an e is in the bottom, but we do when it's in the top. So there's that classic give it a negative exponent. to bring it up. So integrating dv gives us v equals. The integral of an e to the x is itself, but we did have that special case of the formula where if there was a coefficient here, you had to divide by that coefficient. So this is e to the negative x itself divided by the derivative of the, I'm sorry, not the derivative, I don't want to say it that way, the coefficient of the exponent, -1, which is just negative e to the negative x. I need a minute to blow my nose and cough. Must have kicked up some dust particles. Okay. So since I kind of wrote that weird, let me just write it all together here. V is negative e to the negative x. And you might say, well, why don't you bring that to the bottom? Because I'm going to ultimately integrate that. So I'll write it both ways, or v equals -1 over e to the x. You'll see it both ways ultimately. All right, so going back to the original problem, the integral of x plus 1 over e to the x dx becomes, and again, I'm not plugging things into this, I'm plugging them into that formula. And one more time as a reminder, the integral of v du is uv minus integral v du. There's a lot of bounciness to our calculus formulas. It's kind of going back and forth. V du, sorry, v du. I said the same thing twice, didn't I? That's udv on the left. I just always have the right version stuck in my head. It's the integral of u dv, because that's based on, we said u and dv. So u dv is uv minus v du. There's this bounciness. If one of the sides is u dv, the other is v du. The term that's already integrated is the u and the v. No differentials, and it's got a minus to it. All right, and the bounciness of it is because it was derived from the product rule. All right, so integral of x plus 1 over e dx dx. U times v. U is the x plus 1 times the v, which is the negative e to the negative x to the -1 over e to the x. Now, I'm going to have to wrap this first bit in parentheses because of that. Probably going to need the second bit in parentheses as well because it's a negative. So negative e. I'm not sure which to use yet, or the students might not be sure which to use yet, so I'm going to use the original negative e to the negative x. Now, I'm not going to integrate this, so spoilers, I will switch it to this one very soon. Minus integral, then v du. So the integral does not have either of the original bits. It doesn't have the u and it doesn't have the dv. It's got the v and the du, the bottom. So the original integral parts that we use to determine the substitution, neither of those should be in that last integral. That's another way that might help you memorize things. This bit should always be the last bit from each of these. So v and du. The v was the negative e to the negative x. Oops, wrong color. And then the du was just dx. It's really nice when the differentials are the same exactly. That happens when your u is just a linear x and maybe a constant with no coefficient here. If this was a 3x, there'd be a 3 there. It would just change it a little. Let's clean this up some. The negative, let me write out front. The x plus 1, whether you write that in the front or back is up to you. But I kind of like to write it in the back because, well, there we go. My e to the negative x, I'll fix up soon. Here's the x plus 1. Again, all I've done is just swap the order of these two things because it feels better to write the monomial part first. Then minus the integral. Well, that's a minus and that's a minus. Those two cancel, so you just get a plus integral e to the negative x dx.
Okay, so this is going to become, this has already been integrated, so let me bring that to the bottom. So negative parentheses x plus 1 over e to the positive x. Then plus the integral of e to the negative x is just that thing, e to the negative x, but then divide by the coefficient of the top. So plus e to the negative x over negative 1. And then we do a plus c here. And I did something intentional, and that was that I have this in the bottom now and this in the top. You might not recognize these, there's some like terms going on here. Let's bring everything to the bottom now. This negative, let's bring that to the top, so we'll make that a minus. Again, this minus I'm just going to bring out here. The e to the negative x I'm going to bring to the bottom, make it a positive x. So this is negative parentheses x plus 1 over e to the x plus, minus 1 over e to the positive x. So again, the negative 1 in the bottom made the coefficient negative. The negative 1 in the exponent is why the e to the x is down the bottom and has a positive exponent. Then our plus c. Now, believe it or not, there are like terms here. As this is set up, nothing combines, but if you were to split apart this top fraction, you'd have, ignoring the sign, an x over e to the x and a 1 over e to the x. 1 over e to the x is the same as 1 over e to the x. So we need to separate this or split the fraction, then combine like terms. This is not an acceptable final answer. So that's negative x over e to the x minus 1 over e to the x. That was me distributing the negative to these two terms. The e to the x was in the bottom of the combined thing, so it should be in the bottom of them separated. First term, second term. Then this one right here is what was originally there, the 1 over e to the x. So this third one I just wrote is what was originally the second bit. And then you'll have your plus c after it. Now this term and this term, the second and the third terms, are literally the same thing. This is like negative a minus a, 1 over e to the x, 1 over e to the x. We combine those. Negative 1 minus 1 is negative 2. So what we ultimately end up with is negative x over e to the x minus 2 over e to the x plus c. Some people might recombine these and say, oh, well, they both have a factor of e to the x in the bottom. So we could do negative parentheses x plus 2 over e to the x plus c, or negative x minus 2 over e to the x, again, plus c. Oop, I don't want to do that. Let me give it a little more room because that was bad. Negative parentheses x plus 2 over e to the x, then the plus c, or you could say negative x over e, minus 2 over e to the x, and then your plus c. All three of those are the same answer. All three should be acceptable, but you have to be able to recognize that. Some people might combine like terms while they're still e to the negative x's. That is an option. This is not the only way to have completed this problem. It is very rare that I give you an only way to complete a problem because that's how calculus works. They're usually just the best ways, the easiest ways, so to say. Okay, let's do one more like this. So that was D. And I'm going to run out of room, so let me just put it here, E. This is a longer one. Yeah, I know what you're thinking. Longer than those. Oh, you're going to hate me in a minute. The integral of x plus 2 times x plus 4 raised to the 5th power dx. Man, oh man, you are not going to like me now. So if you try regular old substitution, well, first of all, you got two kind of inside bits. That's a bad sign. Not a sign that it fails. But if you say let u be the inside of the complicated bit, that's x plus 4, the derivative is just 1, that's not going to cancel the x plus 2. Substitution is going to fail. I leave that up to you to try out. Try doing it wrong. Trust me. It will be good for you to see how it fails. So we're going to our substitution technique. Now we've been saying to let u be the simpler bit and dv be the rest. What do you think is, now again, a traditional substitution technique, I'd be attacking the x plus 4 because it's the inside of the complicated bit. This integration by parts, it's usually just separated into a part A, part B kind of thing. So x plus 2 versus x plus 4 to the 5th. Which one looks simpler? Because that's what we should let u be. I'd say x plus 2 looks simpler than something that would be like a chain rule as a derivative. Also, that's a spoiler for later. So we're going to say let u be x plus 2, and then dv will be the rest of it, which I'll write in a minute. We're going to take the derivative. This is going to be very similar to last time. Du over dx equals 1. The derivative of x is 1. The derivative of 2 is nothing. Multiply both sides by dx, and you get that du is equal to dx. So we'll let dv be the rest, which was the parentheses x plus 4 to the 5th power dx. And then we're going to integrate that. So the integral of dv equals the integral of x plus 4 raised to the 5th power times dx. Give me a minute. Sorry, family stuff. Okay. So we integrate. Okay, well, the integral of dv is v. The integral of x plus 4 to the 5th, that's why I was going, well, that's not a straight up polynomial rule. You could take this x plus 4 and multiply it by itself 5 times and spend 15, 20, 30 minutes of your life wasted, wasting time on that. But it works. It's just a matter of, I'm gonna have to mute in another 20 or 30 seconds again, just FYI, maybe sooner. Yep, sooner. All right, so when you look at this integral, it's not a straight up power rule. It's not an exponential rule. It's not a logarithm rule. It's not any of those normal basic rules. It's not a constant rule. So that means we need one of the more advanced techniques. So, well, substitution is supposed to be the first thing that we try out of substitution versus parts. So we try substitution. So that's why I said this problem was going to be a really long one. You've got integration by parts as the core of the example, but then inside of it, you've also got to integrate with a substitution. So ... you have to use a substitution to figure that part out. So let's go to the side and do that as its own problem. So to find v, we got the integral of x plus 4 raised to the 5th dx. We would want to say let u equal, so we're back to the substitution technique, so that's the inside bit generally, x plus 4. Now this is a different u from before. You have to be very careful. Maybe you even want to use a completely different color than before. In fact, I'm going to do that. That would have been a really good idea. So let's go with green. So the integral of x plus 4 to the 5th dx. We're going to say let u equal x plus 4 so that du dx is equal to 1. Actually, the derivative of x is 1. The derivative of 4 is nothing. Multiply both sides by dx, and you get du is equal to dx. And normally we'd have to divide by whatever's next to dx, but it's solved. So dx is equal to du. So remember that the things that we're going to plug in are, we're going to plug u in for x plus 4, and we're going to plug du in for the dx. Again, there could have been something else sitting next to the du, it just didn't happen to be that time. So the integral of x plus 4 to the 5th dx is going to become, That's now u to the 5th. The x plus 4 is the u. And then the dx is du. Well, we can integrate this. The integral of u to the 5th is u to the 6th over 6. Now, yes, there's traditionally a plus c, but we just leave the plus c till the very end for all these integration by parts problems. But we don't want to stick this in u. First of all, this u is different than this u. Probably should have done a different letter to be clear, but at least I use a different color. So we have to go back to what u really is. It's x plus 4. So this is really x plus 4 raised to the 6th over 6. This is our v. V was the integral of x plus 4 to the 5th dx. That's what we just did. So this is our v. So let's write everything down that we have now. We know that u is equal to x plus 2. We know that du for the original problem is equal to dx. We also know that dv is x plus 4 to the 5th dx. And we now know that v is equal to x plus 4 to the 6th over 6. Those are the things we'll plug into uv minus v du. The integral of u dv equals uv minus integral v du. So finally we can say our original integral of x plus 2 times x plus 4 to the 5th dx. That was the u dv. dx is equal to formula uv. Here's the u, here's the v. So x plus 2 times x plus 4 to the 6th over 6. U v. And minus the integral of v du. V is again x plus 4 to the 6th over 6. Du was the dx. I love this problem. I really do. Look at this right-hand side. Look at this integral. How much do you hate me right now? Because that integral needs a substitution. We don't have a formula for that. Now, here's the thing. With enough practice, you'll start recognizing forms, and it's not all parentheses raised to an exponent. You just increase the power by 1 and then divide by that same new exponent. It's because of the fact this is just x plus a number, or x minus a number. If I put a little 2 right here, it changes. If I put an x squared right here, it changes drastically. So for this last integral, we need to, again, go to the side, and let's use, how about purple this time? So the integral of x plus 4 to the 6th over 6 dx. You're going to say, no surprise, let u be x plus 4, so that du over dx is equal to 1. Multiply both sides by dx, and you get du is equal to dx, a coincidence. So the integral becomes that's weird. All right, the x plus 4 is now a u, so that's u to the 6th over 6. The dx is now a du. We can just bring the 6 out in front if we like. Again, you don't have to. The integral of u to the 6th du with a 1/6 in front. You can leave the 6 in the bottom and just know it doesn't affect you. Then you can straight up power rule this. That's u to the 7th over 7. So that's 1 over 6 times u to the 7th over 7. But now we have to go back to what we just called this u, which was x plus 4. So that's the 6 times the 7 in the bottom will make a 42. So x plus 4 raised to the 7th over 42. That is this integral right here. There's a minus in front of it, so be careful, don't forget that. Again, this bit right here is what we just did in purple, and we got this, and of course there would be a plus c to the side because this will be the final integral. Okay, so our original integral. Which was x plus 2 times x plus 4 to the 6th over 6 minus that integral of x plus 4 to the 6th over 6 dx is going to become x plus 2 times x plus 4 to the 6th all over 6. You can write that as one big fraction. So this bit right here is what I just wrote. That's this. Then minus, and we just got our integral. It's x plus 4 to the 7th over 42, and now we have our plus c. There's not really a lot that we can do to this necessarily. So I really do expect some people to stop here. But the problem is, if you actually go through and clean this up, if you take a GCF out, this does become much prettier. This does become much nicer. There is a GCF of x plus 4 to the 6th. That is in both terms. It's in this one, and it's in this one. There's 7 here. We can only take 6 of them, though, because the first one's got 6. So we're going to factor that out. So the original problem becomes, we're just factoring that out. We're taking x plus 4 to the 6th away. So x plus 4 raised to the 6th. And some people will take a fraction out as well. I'm gonna pause on that idea though. And because of the extra parentheses, I'm gonna open up a bracket. It's probably a better idea. From the first one, we're left with x plus 2 over 6. Whether you keep that in parentheses or not is up to you. Then minus x plus 4 over 42. Now, the minus in the fraction, that minus is supposed to be distributed to that, so maybe a parentheses is a better idea for this one. That's up to you. And then your plus c. Well, you can distribute your negative, and then you can get an LCD from there. So this is going to become x plus 4 raised to the 6 times. Let me just go ahead and separate the fractions as well. So x over 6 plus 2 over 6 minus x over 42 plus 4 over 42. And the plus c to the side. Sorry, it's kind of squished in there. Well, you might say, oh, well, 2 6 reduces to a third, 4 over 42 reduces to 2/21. That's fine. But let's just get an LCD across all of these for now. Let's just bump all these up to a 42. Admittedly, you don't have to. There is another way to do it, but reducing these is not a good idea because you'll be combining like terms. So you want to get an LCD, which for the x's is 42. For the x's, for the constants, admittedly, it's 21. But let's just go with 42. So LCD of 42. So this becomes x plus 4 raised to the 6th bracket. So LCD, 6 goes into 42 7 times x is 7x. That's 7x over 42 plus 6 goes into 42 7 times 2 is 14. So that's 14 over 42 minus, the others already have it, x over 42 plus 4 over 42, bracket, then your plus c. Combine like terms, the parentheses at the front stays the same, x plus 4 to the 6th, bracket. 7x minus x is 6x. So that's 6x over 42. And then maybe minus, maybe plus. 14 plus 4 is 18, so plus 18 over 42. Then your plus c. Let's go ahead and just write that as one fraction and reduce as much as possible. If you do, you'll get 21. So 3x over 21, and then 9 over 21. X plus 6 to the 6th bracket So again, what I'm trying to say here is 6x plus 18 all over the 42, and then reduce as much as possible. C, final answer coming up, x plus 6, x plus 4, I gotta fix that. X plus 4, I'm going too fast. Oops, draw. X plus 4 to the 6th, bracket, which could really be a parentheses now, and 2 goes in all of those, so that's a 3x. I know I made an error somewhere, didn't I? This is not a number I'm looking for. I messed up my distribution. I pointed it out and then I did it for like myself. This minus was supposed to be distributed to the x and the 4. So this is supposed to be a minus, 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 which makes this number change. I'm going to give you a second to catch those errors. Fix those errors, but everything that I just, again, this minus is supposed to be distributed, so that this 4 should be a minus, minus, and that makes that 18 actually a 10, not a plus. It just makes the 18 different when you combine them. So follow me carefully. Let's erase. That plus and that plus should be a minus. This 18 should be a 10. So again, minus 4, so that stays a minus 4. Then 14 minus 4 is 10. 10 and 42 reduce to 5 and 21 when you reduce them. So that's plus 5 over 21. And of course, your plus C. One of the hardest problems we've done. There's about 10 problems in this whole course that I'd say are the most difficult, and this is one of those top 10. Because you had to integrate by parts. To complete that, you had to integrate by substitution, and to complete that, you had to integrate by substitution. This is not a fun problem, but this is a realistic problem. This is something that somebody in economics or finance or science could just come across in their analysis, maybe. Because maybe their supply curve is this really odd, interesting polynomial product. Or maybe this is used to approximate a virus's growth in population over time. It's not quite exponential because it is a polynomial, but we can use polynomials to approximate exponentials under a short-term time length. Lots of colors, lots of issues, lots of work involved. Let me tell you, this is not a fun problem. This is not an easy problem. This is a challenging problem. I used to always put a problem like this on the final because of its ultimate importance. I don't know that I'd go this deep in it, but please understand that on the final exam, you could see a problem that you have to integrate by parts and then do a substitution once, maybe. I don't know about twice, and if I did it twice, it would be just like this problem. I can guarantee that. But for most of the problems, it's just a substitution or just integration by parts. But again, point of this, when you do integration by parts, maybe you gotta do substitution as well. When you do an integration by substitution, there's actually ways to integrate by parts from there, but it's just weird and wacky and we don't do that. When you integrate by parts, maybe you have to integrate by parts again. There are plenty of problems out there like that. In particular, just kind of a special memo. If you wanted to do the integral of x squared e to the x dx, now earlier we did x e to the x. And that was last class's problem. The integral of x e to the x, we integrated by parts one time and we got the answer. This problem in particular requires integration by parts twice. When you get to your uv minus integral v du, that integral v du part is going to end up being, no joke, there's another constant or a sign in there somewhere, but no joke, it's x e to the x. So you end up having to do it twice. Now what you could do is you could say, well, I already did that problem earlier and I know that the integral is this thing right here. So let me just go ahead and bar that information. And on a test, that's exactly what I would expect you to do to save yourself some time. So point being, this could be a theoretical test question that involves two integration by parts. In order to do that, though, what I would do on the test is I would make x e to the x a problem before it, and then later you see this one and you can just borrow a previous answer. And that would be perfectly fine. So you don't have to reinvent a wheel for part of a problem. That's what mathematicians like to do. Borrow information. Okay, so those were all indefinite integrals. We've also seen definite integrals, so what do we do? Definite integrals needing integration parts. Do the evaluations on the UV part as well as the integral of VDU. So when you're doing a definite integral, the only thing that changes is you're not just going to plug in your upper and lower limits to the very last part you integrate, because remember that when you get that UV, you actually integrated to get the UV. It was part of the integrating dV bit. So because you've integrated to get the UV, you have to evaluate the upper and lower limits there as well. So the formula just changes very minorly, and it changes to this. The integral from A to B of u dv is equal to uv evaluated between a and b, so you plug in the b number, then subtract plugging in the a number, minus the integral from a to b of v du. So you have to integrate this part and then plug in the upper and lower limits. Now what's funny is there's a minus in front of this. So plugging in the upper limit actually ends up getting subtracted ultimately when you see the math happen. And then plugging in the lower limit, because there'll be a minus for that, and this minus they cancel, and you end up adding it. It's kind of weird. Don't focus on that aspect. Focus on the fact that there's a negative that has to be distributed, that your teacher almost goofed up on in a previous problem, but paid attention and caught it. We're only going to do one of these examples. So let's do the integral from 0 to 4. And again, I say you have to memorize this, but there's really not much variation in what you already memorized. The u, dv, uv, vdu pattern is the exact same. It's just plug in upper and lower limits. I don't really think I need to call that a formula in my opinion. So let's go back to one that we dealt with, well, last class, one that I just referenced. The integral of x e to the x dx. Now I know I just said there's no real need to reinvent the wheel, but we did do this last class, so let's reinvent the wheel. And it is, there's a little bit of difference here with the upper and lower limits, so I think it's just a good idea to practice. So we know that regular substitution will fail because these things aren't a power off of each other, so we got to go to this integration by parts. So we'll say let u be the simpler part, which is x, which makes its derivative 1. Multiplying both sides by dx gives us du equals dx. Then dv is going to be the rest, so dv is equal to e to the x dx. We integrate both sides. Whatever you do to one side, you do to the other. Integrating dv will always give you v. Integrating e to the x will always give you e to the x. There's no extra coefficient in there, so there's no divided by a number. It's a 1. Dividing by 1 does nothing. And you might say to put a plus c here, but A, we always just wait till the last minute with the formula to do that. B, we're actually doing upper and lower limits. So since we're finding the area between a curve, we don't need a plus c anywhere. No c in this problem. So again, the three things that we need are the u, the v, and the du. Those are the three things we'll be plugging into this formula. So what we can say is the integral from 0 to 4 of x e to the x dx is equal to, now you might think, all right, well, you're doing substitutions, you need to turn these into u's values or whatever. but we never actually write u anywhere. This is just to clean up the problem and plug it in for a formula. That's the difference of substitution versus parts. Substitution, you actually do see the integral with u's, whereas integration by parts, you never do. So uv, I don't write uv, I write x times e to the x. That's the uv. But now plugging that in between 0 and 4. And see, I'm still in my American dollar, so I don't switch those numbers. Minus integral from 0 to 4. V times du, v is e to the x, du is dx. So e to the x dx. Once again, we've gotten a simpler integral, one that we actually know how to integrate, unlike the last problem, where it took us a couple of times to get there. Before we do the evaluations, let's just wait till the last minute to do all of those. Let's do the integration. The integral of e to the x is e to the x. Again, literally saw it right there. So this is x e to the x evaluated between 0 and 4 minus, now I might want a parentheses or a bracket because of the minus part, so minus parentheses. The integral is e to the x evaluated from 0 to 4. And again, you might say you don't need that parentheses, but I have a feeling a lot of people will mess up their signs moving forward if they don't put that parentheses there. Okay, and again, evaluated between 0 and 4. So let's plug in 4 and 0 to the x e to the x. So this is the plugging in of the 4. When I plug in the 4s, I'll do it in red. When I plug in the 0s, I'll do it in blue. So this is 4 times e to the 4 minus 0 e to the 0, then minus, and parentheses because we're plugging in the 4 and the 0 into the e to the x, but this minus is outside of that plugging in. That's why I suggested parentheses might be helpful there. So red, e to the 4, and minus blue, e to the 0. Now remember that anything to the 0 power is 1. But 0 times anything is 0. So this is really 4 e to the 4th minus 0. Let's distribute the negative. So that's a minus e to the 4th plus 1. The e to the 0 is 1. Did not mess up my distribution this time. Minus 0 doesn't really need to be written, so we're just not going to write that second term. And the first and third terms are like. This is like having 4x minus x, because they both have e to the 4th as a factor. So 4 minus, there's a 1 imaginarily there. 4 minus 1 is 3. So this is 3 e to the 4th plus 1, and that's our answer. If this was an application, you might want the approximation to that, which is 3 e to the 4th. Plug it in on your own calculators. I don't want to have to pull up mine. It takes a couple minutes. Actually, I lied. We're going to be ending class early, a few minutes early anyway, so let's do it. Calculator, calculator, calculator. So that problem was 3 e to the 4th, so 3 e with an exponent with a 4, or you can make the exponent yourself. Close the parentheses, then not minus 1, plus 1. And we get 164.79, so let's round to the nearest tenth, so 164.8. Or if you round to the nearest whole, about 165. Again, if this was an application, maybe we were finding the area under a curve. Maybe this right here is our profit curve, our profit rate per day. So how much profit we make each day, and then we can integrate from 0 to 4 days to find how much profit we made in 4 days, or 4 years, whatever the time scale was. So we made 164.8. I don't know, is this in dollars, hundreds of thousands of dollars, millions of dollars? Again, it's not an actual application problem, so there we go. I just wanted to give you a setup, an idea for that.
All right, So that closes out that section, 4.6. So we're going to get into 5.3, improper integration, which is a very, very, very lengthy section. It's a pretty heavy-handed technique. If you thought the UV substitution thing, the integration by parts, was heavy-handed, this is equally up there. They're both amazing integration techniques, and it can be a challenge trying to figure out which one to use at first when necessary. But really, there are a lot of good patterns, and with repetition, you learn the patterns and you learn when to try one or try the other. But the biggest, the most important fact is if you try one and it doesn't work, you probably need the other one. Now, again, this is for the more complicated integrals. If something fits a basic formula or something else, that's of course not the case. All right, so here we go, 5.3, improper integration, and we'll have a break in about 30 minutes.
Okay. So improper integrals are such that either the endpoint, one of the endpoints, is an infinity, or the function value at one of the endpoints is infinity, is n infinity. Now, when I say n infinity, I mean plus or minus. So improper integrals are when this function shoots up forever and ever and ever, so that's an asymptote, or shoots down forever and ever and ever. Or if we're just going to integrate from, say, 0 to infinity, or negative infinity to infinity. It's not that one of the endpoints has to be an infinity, both can be as well. So we're no longer talking about finite regions. And the first thing you think is, oh, well, if you do an infinitely long width, the area has to be infinity, right? I mean, just think about all the different integrals we've done before. So if we have, say, a quadratic where our function looks like this, if we were going to integrate this thing to infinity, the area just keeps getting bigger and bigger and bigger and bigger and bigger. So if you integrated this from, say, 0 to infinity, this area would actually be infinity. If you did the integral from 0 to infinity of x squared dx, this would turn out to be infinity. And you can see this geometrically because as you go further to the right, the area gets bigger because the function is higher and higher and higher. So maybe up to a certain point, the area is 1,000. Just go further and it can be 10,000. Go further and it can be 1,000,000. Go further to the right and it can be 10 million. Go further to the right and it can be a trillion, a quintillion, a septillion, a nontillion. That's 9. 9 of those things. So the further you go right, the bigger the area is, and every time you go right, the area gets bigger and bigger and bigger and bigger, and the rate of the area increasing is getting bigger and bigger and bigger. So that's why this area is infinite. It's not really logical to find that area. But what we can have happen is, what if instead of this thing growing to the right, what if it decayed? So what if our curve looked more something like this? Now this area got some decent area over here, and in fact this is part of the graph of 1 over x. I'll write that to the side over here. Or 1 over x squared. I don't want to say which one. 1 over x to the n, because what that exponent is will cause some issues, as we'll see and discuss. But this function, as you go wider and wider, it's getting shorter and shorter and shorter in height. It is possible this area is not infinity. So the integral from, say, 0 to infinity of 1 over x to the n. That's what we're doing here. I'm saying maybe it's not infinity because the heights are getting smaller and smaller and smaller. So even though you'll go to infinity in width, maybe this height is shrinking quick enough that all these areas over here are so microscopic in size that they don't really affect the area. In other words, most of the area is seen in this region right here. And that all this stuff maybe only adds 1 or 2 to the final area or some small number. But believe it or not, it's possible that this thing doesn't drop quick enough. That's why I said it's possible this area is not infinite. So if the height of the function doesn't drop quick enough, which is a very loose statement, how quick does it have to drop? We can't even determine that. We just have to try and do the integral. So if the height of the function doesn't drop quick enough, then the area still infinity. You must try integral to see what happens. But the problem is, how in the world do you plug infinity into a function? You don't. You instead just need to know the behavior of that function at infinity, and guess what? This goes all the way back to the first week of class when we were taking limits. Sometimes we were doing the limit as, say, a function went to 5. Sometimes we were doing a limit as a function went to infinity, and we had to look at the end behavior of the function, and we classified that, based on a couple of different features, which we will reiterate those features very, very shortly. So we will need limits. To quote, plug in infinity. Again, we don't really plug in infinity. We just think about what happens at infinity. And it's usually either 0 or infinity. It usually either goes to 0 or usually goes to infinity. There are cases where they don't. But we won't be dealing with those exceptions for single polynomial terms. So, for example, if you had the integral from some starting point a, so this a would be a number like 0 in the last example, and we were going to positive infinity. And this was just some function that was given f of x dx. You would have to go and change this to a limit as b goes to infinity. We'll call b the upper limit now, and then integrate from a to b. So we won't plug infinity into the function. We'll do the integration. We'll plug in b and a, and b will literally be the letter b. But then we'll say, okay, well, if we think about b becoming extremely large, if it goes to infinity, what would happen to the term that has the b in it? Is it 0 or is it infinity? So we have to know that. So we're only able to evaluate this if the limit exists. If it doesn't exist, that means the area is probably infinity. So let's remind us of a couple of different limits as certain things go to infinity. So reminders. What is the limit as x goes to infinity of 1 over x to the n? Where we're going to assume that n is positive. So it doesn't have to be, but there's 2 different answers. Whether n is positive or negative here, you get 2 different answers. So I'll split these into cases. When it's negative here, I'm going to write it a different way. All right, so x is the thing that's in the bottom, and this is a positive exponent, which means the bottom is going to be getting bigger and bigger. Just think about if the n was a 2. So 1 over x squared. Think about your x getting bigger and bigger. 10. 10 squared is 100. 1 divided by 100 is 0.01. All right, well, what if your x was 100? 100 squared is 10,000. 1 divided by 10,000 is 0.0001. I think I may have said 1 0 too few, but you get the point. If you put in 100,000 and a million, that output is just going to keep getting smaller and smaller and smaller. We did this at the very beginning of the semester. This limit was 0 because the denominator keeps getting bigger and bigger and bigger. Dividing by a bigger and bigger and bigger and bigger and bigger number makes this thing smaller. You can see this graphically. Just do 1 divided by x squared. Again, I'm picking a particular n, but the bigger you make n, the more obvious this becomes. See, look at this. As your n gets bigger, this thing just goes to 0. It goes to 0 very quickly, in fact. Trace. All right, it's at 1. At 1. Then it's at 0.15 by the time you get to 3, 0.1, 0.01, 0.02, 0.011, 0.009. I mean, it's going to 0. We've done this stuff before. Hold on. Okay, had to cough there. All right, limit. What if it was the other way around? What if it was the limit as x goes to infinity of x to the n, where n is positive? This is basically flipping the script on the previous case. So I'm only trying to think about positive exponents here because numerically that's the only way we can think. When we see negative exponents, we just flip them around to do calculus or to make the algebra clean. So that's why I'm not trying to think about these with negative exponents. But this right here, this x to the n with n being positive, that would have been 1 over x to the n with n being negative. So again, this second case right here is the first case, but just flipping the direction of the inequality here. So what if we had an x squared or an x cubed? What happens as x gets bigger and bigger and bigger? Well, let's just go to x squared. If you plug in 10, that squared value is 100. If you plug in 100, that squared value would be 10,000. If you plugged in 1,000,000, that squared value would be 1,000,000,000,000. This thing gets bigger and bigger and bigger and bigger and bigger. This limit, you could either say is infinity, or much preferred to me, does not exist. Now, I actually have to make a special memo here. I forgot to mention, also the n can't be 1. If it's 1, actually I take that back. No, it doesn't. Even if it's the first power. So those are our polynomial terms. This is something that you should be really familiar with, in my opinion. You might need to dust it off, but we did talk about these very heavily in the beginning of the semester. But you'll also see this stuff come up with exponentials and logarithmic terms, so we need to consider them as well. So what if we had the limit as x goes to infinity for e to the, and I'm going to write this one. I know I just said we don't like to think about it this way, and so I didn't on the left one. But really, we don't like our exponential terms in denominators for calculus, so this is the better way. And I have to say that a is positive here. And I don't want to write it right there. Actually, yeah, it's fine. So this is a positive number, meaning that the coefficient is negative here. So as x gets bigger and bigger and bigger here, this exponent's going to get smaller and smaller in terms of negatives. So if you plug in, say, x is 100,000, let's say the a is 1. So this is now e to the negative 100,000, which means you have to do 1 over e to the positive 100,000. And that falls in line with this. You're going to be dividing by a really, really big number, which makes this a very, very small number. This limit ends up being 0. If you don't trust that, calculator, let's just do e to the negative, and I can make up any positive a value. Let's do e to the negative 3x. Let's see what happens here. Look at that. It fell really quickly. If you trace it, by the time you're at 1.7, you're already at 0.006. And as I keep moving right, these e's just means move the decimal left that many times. So this is 0.00013. Now we're at 0.0000079, blah, blah, blah. I mean, this thing is just practically writing the x-axis. That's that horizontal asymptote we see with exponential decay functions. So that limit goes to 0. But what if there wasn't that negative there? So we're going to keep the a positive still. If this was a positive number, so now the exponent is ultimately positive, I can just delete the negative. This should be exponential growth, which we should all be familiar with. And this thing grows up and up and up. And if you trace it, I mean, by the time we're at 2, it's already at 312. By the time we're at 5, we're at 450,000. No, I'm sorry. Is that millions? There's million. 4 million and some change. Wow. By the time we're at 10, we're at 1 times 10 to the 13th. So that's a 1 with 13 zeros after it. As a big number. So this thing is going to infinity, so we say does not exist. There are 2 words we can use with going to 0 or going to infinity. We say convergent or divergent. When we converge, that means that the answer is finite. When we're divergent, that means it's infinite. And those are very, very common terms used in advanced calculus that we're not going to get into studying, but the concept of convergence and divergence is really important when you're trying to approximate functions. So like when we're doing those rectangles to approximate the area under a curve, it's very important that those areas are close and that the more we do, the closer we get. That's an idea of convergence. If for some reason we did more rectangles and it made the area a worse approximation, which believe it or not, can happen for weird classifications of functions, that would be divergent. And again, there's an entire field of mathematics on convergence versus divergence. All right, so there's our exponentials. What about our logarithms? The limit as x goes to infinity, and we only do the natural log in here, just like the natural exponential. Now remember, if you take the inverse of an exponential, you get a logarithm. So if you flip e to the ax across the line y equals x, you get the graph of natural log. Remember, e to the x looks like this. And then the natural log of x, again, if you flip that across the line y equals x, what it ends up looking like is something like this. So e to the x has a horizontal asymptote on the left side when it's growth. If it was decay, we'd flip-flop it. So the natural log has a vertical asymptote at 0. Remember, you can't plug 0 or any negative numbers into a natural log. Hence, when we integrate, we need the absolute value. But that quick growth of exponentials is instead slow growth for natural logs. But this is not an asymptote. This right here is not an asymptote, which means it's not flattening out, it is growing. It's just growing very, very slow. It's the tortoise versus the hare kind of situation. Not necessarily with the moral that the tortoise beats the hare, just in that one's growing quicker than the other, or one's moving quicker than the other. So because this thing is going up forever and ever and ever and ever and ever, even though it's going slowly, it will hit eventually infinity, so its limit also does not exist. So there's only 2 of these scenarios that I'm giving you where a limit exists, and that means that you could actually find the area. So guess what? Those are the 2 most common scenarios. We are most commonly dealing with this one and with this one. That was a weird highlight. I'm not saying the others don't come up. You can most certainly get divergent areas, infinite areas. I'm just saying that because most of the answers are finite, we usually deal with those 2 highlighted scenarios. So if you're going to skip ones to memorize, I'd skip these 3 and memorize these 2. But really, if you memorize one, the other falls naturally. If this limit exists, the other one doesn't. If this limit exists, the other one doesn't. Also, if you don't trust my graph of the natural log, quick reminder, natural log of x, boom. There's that slow growth. Again, there are functions that asymptote to a specific vertical height. Rational functions, things like 1 over x minus 5, or 3x plus 2 over 7x minus 1, that one more in particular. That thing would actually taper off to a specific height. We've kind of neglected rational functions so far. That's one of the things I'm kind of thinking about discussing next class. That's one of the 3 main topics I'm probably going to circle back to. I just got to figure out which of those 3 I want to, or if I have time, maybe 2 for a lighter discussion. All right, so let's try this out. Let's see what we're doing and see where it goes. Whoa, whoa, whoa. Also, I just realized that since you didn't see my screen for the first 5 or 10 minutes, and I'll do this again at the end. Here's those notes that I mentioned. Thankfully, I said all the dates out loud. But there they are. Maybe snap a quick picture of this if you have to, or a screen grab, or just remember where it is in the lecture. But again, I'll do this at the end just like every single other time I have. At least I hope I have every single time. Okay, example 1, evaluate the improper integral. I'll just write it here. Please pay attention to how MyMathLab wants you to answer these if it is a non-finite value. Again, you will have, that looks like integral, doesn't it? There we go. Some of these will be finite answers. Some of these will be infinite. So they may want you to write does not exist. They may actually want you to write infinite, which is really rare that a book wants you to do that. Okay, A. The integral from 1 to infinity of 1 over x squared dx. The dx could be in place of the 1 or to the side. It doesn't matter. We've talked about that many times. So this is an improper integral. How do I know? I see an infinity here. There are improper integrals that do not have an infinity in them, and that's because they have vertical asymptotes somewhere in them, if not the end, somewhere in the middle. So there are times when you'll have to do this, potentially, in all of calculus, where the limits aren't actually infinity. But all the examples I do, it will be that way. I promise. Okay. So because of the infinity, we have to change this up. We have to say equals the limit. And what letter you write here does not matter. You can do B, you can do A, just don't do X, you can do Z. So the limit is B goes to infinity. So we want to think about this number B getting really, really, really big. And we're going from 1 to B, or 1 over x squared dx. Okay. Well, we know how to integrate 1 over x squared. When you looked over here, it was terrifying because, oh, infinity, well, what do we do? That's got to be an infinite area, right? Right? Question mark, right? Maybe? Voice is getting higher? Okay, well, let's ignore the infinity part. And let's just think about, what if this was a number? 1 to 5, or 1 to 50, or 1 to 5 million, or 1 to 5 trillion? Just think if this was a number. So now all I got to focus on is this part. I'm going to ignore the limit now. I'm going to keep writing it until I take the limit, but I'm still ignoring it, basically. So this will be equals the limit as b goes to infinity. And then I don't know how to integrate 1 over x squared in this format because the x is in the bottom, but we know how to bring it to the top, make it a negative exponent. So this would be the limit as, oh, I forgot my integral symbol. 1 to b of x to the negative 2 dx. I don't need that 1 anymore because it would just be a 1 here, which is unnecessary. Now we know how to integrate this. We use a power rule. Now if that had been 1 over x, it would not be a power rule. It would have gone to that natural log with an absolute value. Spoilers for later. All right, so equals. We're not doing the limit yet, so write it. But now we're going to integrate. So we add 1 to the exponent and divide by the same value. Negative 2 plus 1 is negative 1. So that's x to the negative 1 divided by negative 1. And we're evaluating this between, there's no plus c needed, 1 and b. Dividing by negative 1 is the same as multiplying by negative 1. And because we're going to be plugging stuff in now, I don't really want that x to the negative 1 there. Let me do one thing at a time, though. So limit b goes to infinity. Negative 1 times x to the negative 1, evaluated from 1 to b. So again, that's just me bringing the negative 1 from the bottom to the top, changing from a division to multiplication. If that had been a -5 or something, the 5 would still be in the bottom, but the negative could be in the top. But I don't know how to evaluate negative exponents. So this is the limit as b goes to infinity for -1 over x to the +1 now, evaluated between 1 and b. Now we can plug in the upper and lower limits. The upper limit is the b. We're not taking the limit yet. So limit as b goes to infinity. We're back to that stuff. I know it's frustrating, but you have to write it every time or you might forget it. And then you just leave your answer with a b. So -1 over b, that x is now a b. Then a minus to actually show the subtraction upper minus lower limit. And now we're plugging in 1 here, but that's another negative. So minus -1 over 1. So this is the limit as b goes to infinity of -1 over b plus 1 divided by 1 is 1, so 1. We are now at the point where there's no more math to do. This is where we should be plugging in b. Now that b is in the bottom, and it doesn't have an exponent written, so it's a +1. And we said earlier, now we use x's instead of b's. It doesn't matter what letter this is. If you have 1 over something with a positive exponent, when you go to infinity, it goes to 0 because the bottom is going to get bigger and bigger and bigger, which makes the whole thing get smaller and smaller and smaller. Dividing by a bigger number makes this whole thing smaller. So this ends up being like 1 divided by infinity, and 1 divided by infinity is 0. Or again, just thinking as this goes to a million, a billion, a trillion, this division goes to 0.1, 0.01, 0.0000001. It's going towards 0. -0, which is still 0. This +1 here, though, stays. There's no limit to take with a number. It's just when the variables are there. So there's a +1, and 0 + 1 is 1. That says that the area under the curve 1 over x squared with an infinitely long width going from 1 to infinity is only 1. The first time I did that, it blew my mind, or whatever similar polynomial term my calc teacher did. That is crazy. The area under this curve that is infinitely wide is only 1. So what I'd like to do is, using our calculator, let's put that function 1 divided by x squared up here. Let's graph it. And actually, I don't need the negative, so I don't need the left half of this graph, just the right half. So let's go with an x minimum of 0 and an x maximum of, say, I don't know, 100. Let's start smaller, 50. For the y scale, it's all positive, so let's go from 0 to, and we'll keep it small, 5. So this entire graph is over here. And it's getting infinitely high the closer you get to 0. It does have that vertical asymptote feature. But it shoots down to pretty much 0 really quickly. If you trace this, if you start at, say, 0.1, you're at a height of 100. When you go to 0.5, you're at a height of 4. When you go to 1, you're at a height of 1. When you go to 10, you're at a height of 0.01. When you go to 25, you're at a height of 0.0016. So these heights are very, very small. So there's very, 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 very small heights, or at balance are very, 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 very wide widths. All right, so let's go to the calculator section, and let's do 7. That's the integral. Let's just do the area from 1 to 10. So lower limit of 1, upper limit of 10. It was that little shaded region. Look at that, it's 0.9. 0.9. So let's make a little note here. I thought I hit blue. The integral from 1 to 10 of 1 over x squared dx is equal to 0.9. Now, this curve never goes under the x-axis, which means we are only adding to the area as we move on. What that means is 90% of the area of the curve we originally found is just between 1 and 10. The other 10% goes from 10 to infinity. All right, what if you get one, instead of going 1 to 10, let's do a different area. Let's do 1 to 50, since I have 50 up there. I think that's the wrong thing. So lower limit of 1, upper limit of 50. Let's see what this area is. So another 40 more in terms of width. And it's crunching, 0.98. 0.98, and I'm going to round that to 0.98. So 1 to 50 of 1 over x squared dx is 0.98. So 98% of the area of this infinitely wide shape is between 1 and 50. That is because that 1 over x squared function is dropping so quick that from 50 to a million, a billion, a trillion, a quintillion, whatever, is practically nothing. It's only 0.02 at best. You know what's weird? I don't have an example written that I thought I did on my notes. I'm going to do it anyways. So I love the comparison. And you know what? I think I do it just on the board anyways. I don't have it in my notes, but I still always do it. I'm talking and y'all don't even need to hear it.
All right, so we're going to take our break before we start that example that I was just about to do. Let's say be back at 7:59. Let's go ahead and stretch those legs. All right, back to it.
B, we're just going to call it B. The integral from 1 to infinity of 1 over x dx. Now I'm going to go ahead and spoil this. Because not this part, but in regards to the previous part. If I did 1 over x cubed, you'd get an answer. If I do 1 over x to the 4th, you're going to get an answer. If I do 1 over x to the 5th, you're going to get an answer. The bigger the exponent in the bottom, the quicker this function goes to 0. The smaller the area will be. So if 2 works as an exponent in the bottom, 3 is going to be even better. 4 is going to be even better. 5 is going to be even better. A million is going to be even better. But I'm not going bigger in the exponent. I've gone smaller. I've gone to 1 over x to the 1st. So x squared, as well as any higher exponent, would work in the bottom to get a finite area. But let's try this one. So because of the infinite limit, we got to switch this to because of the infinite endpoint, we got to switch this to a limit as b, or whatever letter you like, goes to infinity from 1 to b of 1 over x dx, which clearly we need to make that the limit as b goes to infinity, 1 to b, x to the negative 1 if you want to. Really, I wouldn't do this. Me personally, I would have never done this because I know my rules. But this is just kind of a, hey, maybe you've forgotten a rule. This is what you might try to do since we just tried the same thing. If you add 1 to this, negative 1 plus 1 is 0, and you divide by 0, nope. Remember, that's the one and only one version of the power rule we can't do. Remember, you can't power rule this. This was the natural log case. Remember, the integral of 1 over x dx, or if you wrote it this way, x to the negative 1, is the natural log of the absolute value. So while you can't power rule this, I'm not saying the integral you can't do. You can. We've done it many times. It's just the limit as b goes to infinity of the natural log of the absolute value of x from 1 to b. Now you might say, I know I'm plugging in positive values so I can drop my absolute value. That would be okay since we're doing an area. That would certainly be fine. All right, so this is the limit as b goes to infinity. I will leave it, though, to be technically correct. The natural log of the absolute value of b minus the natural log of the absolute value of 1. The natural log of 1 is 0. Please never, ever forget that. The natural log of 1 is 0. So the second term is gone. It's just 0. So this is equal to the limit as b goes to infinity. The natural log of the absolute value of b, and that's it. Again, that's a minus 0. This part is nothing. It's minus 0, so it's gone. Well, let's think about actually plugging in our b now. If we go to infinity, if we plug it in here, what happens? So again, you've got to think about what the natural log graph does over time if you haven't just blatantly memorized it. The natural log graph grows but slowly, but it still grows forever and ever and ever. We said earlier, the limit of a natural log, as x goes to infinity, does not exist. So this does not exist. It is not a finite area. I love the comparison between these two problems because 1 over x squared does have a finite area, and it's in fact a tiny number as what you might think it is. You'd probably think, well, even though it's finite, it's probably like 1,000,000 or something. Nope, it's 1. But on this one, 1 over x, which again, the shape of the curve is very similar to 1 over x squared. One of the left side's reflected, but we don't even need to worry about that because this doesn't use the left side of the axis, the negative x values, that is to say. But it flattens out slower. So let me just delete the exponent from this. And let's go back to a window from 0 to, I don't know, 10, and a y from 0 to 5. This right here is the 1 over x. This right here is the 1 over x. I'm going to put the 1 over x squared up to compare visually. So now it's drawing the 1 over x squared. See, on the left side, it's actually a little higher on the left side. This right here, if I hit trace, I'm already on the left side. No, I'm not. Let's go to 0.5. Right now I'm on the 1 over x graph, which is this one. If I hit up, I go to the 1 over x squared graph, which is a little higher. At 1, they match. 1 divided by 1 is the same as 1 divided by 1 squared. And then after that, they flip-flop. Remember when we talked about area between two curves? So if I did the area between these two curves from, say, 0 to 4, you'd have to split up the intervals because one of them is higher left of 1 and the other is higher right of 1. But anyways, as you move right, so I'm moving along the 1 over x squared graph. And this is covering it, unfortunately. So let me just change the y values from 0 to 1. So we're really going to focus on just 0 to 1 on the y's. There's 1 over x. There's 1 over x squared. Now you can really see that 1 over x squared is definitely lower. Again, I'm now on 1 over x squared. It's lower. So 1 over x squared, the heights of those infinitely many rectangles is getting very small very quickly. I mean, it's almost to 0 by the time you hit 5. And look at the height. It's 0.04. Let me go to 10. 0.01. So it's 0.01, 1/100th, whereas on the other one, it's 0.1. So this one is 10 times shorter in terms of height, and that effect is going to keep compounding as you go right, and as you go right, and as you go right. So it's just funny because the area under the x squared graph is finite because it drops super fast. But 1 over x, it still drops, but not fast enough for this area to converge if you're going to go to an infinite width. All right, let me get rid of the 1 over x squared. Let's go back to that normal window from before with a y maximum of, say, 10. Actually, we did 50 the first time, so let's go to 50. So, second, calculator. Let's go to the integral. Lower limit, let's do from 0 to 10. 0, enter. 10, enter. Oh, I went from 0 to 10, didn't I? I meant to do 1, and I'm going to break the calculator because it can't handle it. It's, see, break. That's because going to 0, you have that divergence issue as well with 1 over x. I got to go from 1 to 10. There we go. And that area is 2.3. So more notes. The integral from 1 to 10 of 1 over x dx was about 2.3. The integral from 1 to 50 of 1 over x to option 7 from 1 to 50. What happened? Lower limit 1, upper limit 50. Is my window off? Oh, my x max. I have my x maxes and y maxes swapped. The x max was supposed to be 50. The y max was supposed to be 5. Sorry. Okay, now it'll work. It didn't mess up the first integration. It just wasn't letting me do the second one because it wasn't wide enough. Lower limit 1, upper limit 50. There it shades it. And it's 3.9 roughly. The fact that we went from 2.3 to 3.9, changing from a width of 9 to 49, is a clue that this is what we call divergent, especially if you compare it to the previous example. Look at how close these are to each other, 0.9 versus 0.98. By making a much wider integral width, the area value didn't really change that much on the initial part. But here, doing so, now that's still not like a giant change, but it is enough to say, I don't know, if I went to infinity, if I haven't already done this calculation, this is a clue to me that it's divergent. It's not a guarantee, it is a clue. So this bigger gap says that area is probably divergent if you went to infinity. The smaller gap says it's probably convergent. And again, convergent means the number exists, it's finite. Divergent means it's infinite. You can't really think about an infinite area, which is why we just say it does not exist. If we were talking about an application, that would mean we're making infinitely infinite money or something like that, or there's infinite people. Those don't happen. All right. So again, I love this example. And this is actually the largest unacceptable value of an exponent. And by unacceptable, I mean when you want to get a finite area. If this exponent was 1.000000001, this would actually become a finite area with the x in the bottom, with an exponent of 1.0000, and I can say 0 all day long, 1.0000001. All I got to do is have an extra 1 somewhere after a trail of zeros. It would no longer lead to a natural log when we integrated. It would be a power rule. The x would still be in the bottom no matter what. And because of that, when you go to infinity, the 1 over x goes to, or 1 over x to whatever power it is, 1 over x to the 0.00001 would go to 0. So this is like the worst case scenario for a polynomial type term in the bottom. Any polynomial terms in the top, they're automatically divergent. All right, well, what about radical terms? We haven't done too much integration in class with these, but we did plenty of derivations with them, derivatives. So you should still know how to handle your fraction math. They've been in the homework. What if you had the integral of 1 over the square root of x dx? I'm sorry, that's d. Pardon me there. This is supposed to be 1 over the cube root of x to the 4th, going from 1 to infinity. So you know what the next example is. And then dx, of course. And again, to the side or in the top. Well, there's an infinity. And by the way, these can be negative infinity as well. You would just say take the limit as maybe a goes to negative infinity, or b, or whatever letter you like. We just tend to use b to denote an upper limit and a to denote a lower limit. All right, so let's limit this thing. The limit as b goes to infinity, integral 1 to b, 1 over the cube root of x to the 4th dx. There are two major issues with this integrand, that is the function inside of the integral. First being, we don't like to see radicals. We need to convert them to rational exponents. So as a reminder, for about the 10th time I've done it in here, the nth root of x to the n is x to the n over m. So this is really x to the 3/4 in the bottom. I forgot to switch to red there. Limit b goes to infinity, integral 1 to b of 1 over x to the 4/3. I think I said 3/4 the first time, and I meant to say 4/3. The numerator is the power, the denominator is the index, x to the 4/3 dx, which is the limit as b goes to infinity. We don't like the variables in the bottom to actually integrate, 1 to b, so bring it to the top, x to the negative 4/3 dx. Now we can set this up with our power rule formula. Add 1 to the exponent, divide by the same value. I will show all the detail for this one. So this will be the limit as b goes to infinity. It's a terrible looking m. No more integral symbol because I'm actually going to integrate. Add 1 to that, so that'll be x to the negative 4/3 plus 1 divided by literally the same math, negative 4/3 plus 1. I don't need a plus c because we're doing an area. But I got to show the evaluation between the lower limit of 1 and the upper limit of b, which is eventually infinity. What's negative 4/3 plus 1? Negative 4/3 plus 1 is negative 4/3 plus 3/3, which is negative 1/3. Fraction math never goes away. So limit b goes to infinity of x to the negative 1/3 divided by negative 1/3, evaluated from 1 to b. Remember that dividing by a fraction is the same as multiplying by its reciprocal. Dividing by a fraction is the same as multiplying by the reciprocal. In other words, A over B divided by C over D is the same thing as A over B times D over C. If you need to take the intermediate step, you switch the big division bar, sorry, the big fraction bar to a division symbol, then flip and multiply. So dividing by -1/3 is the same as multiplying by -3/1. Limit B goes to infinity. -3/1 times x to the -1/3 evaluated from 1 to b. Clearly, we don't have to show the 1 in the bottom. 3 divided by 1 is 3. But now that we're getting to the point where we want to start evaluating these, now we don't like this version anymore. We can do the math with this version, but nobody thinks this way. We all think in radicals, but we have to change and do computations with rational exponents. So now let's bring the negative to the bottom. Let me just kind of do it here. So that's the limit as b goes to infinity. -3 over x to the +1/3, evaluated from 1 to b, which is the limit as b goes to infinity of -3 over the cubed root of x, evaluated from 1 to b. We're finally getting somewhere. I'll give you a few seconds to catch up. Okay. See, the denominator was a 3, that's why the index is a 3. The power was a 1, that's why this power is a 1, but we don't write powers of 1. All right, we're finally ready to no longer write limit. We're going to plug, well, I mean, sorry, after this next step. One more step. We'll finally be ready to not write limit. So limit, b goes to infinity. And again, this could be a negative infinity if that was how the integral is set up. So -3 over the cube root of b minus, so that minus is the upper limit minus the lower limit. Now let's plug in the lower limit, we're plugging in the 1. Now this whole thing's a negative, so make sure you have that extra negative. -3 over the cube root of 1. Well, the cube root of 1 is 1, so this whole part is just -3, but a double negative makes it a positive. Limit, b goes to infinity. -3 over the cube root of b plus 3. This is finally the point where we will no longer write limit. We are finally going to think about what happens as this b goes to infinity. What happens to the over a cube root? Now, it doesn't look like it anymore, but remember, this was an x to the 1/3. So this is really b to the 1/3. So just as a note, this is b to the 1/3. If you need to see it the other way, here's the alternative version. Again, it doesn't matter which way, you can make the same analysis, but you might have an easier time with this one. What did we say happens if your variable's in the bottom with a positive exponent as you go to infinity? What happens? This thing in the bottom gets bigger and bigger and bigger. It gets bigger very slow because it's a cube root. But cube roots have that same kind of shape as a natural log on the right-hand side. A little quicker growing, though. So this will get bigger and bigger and bigger. We're taking a cube root of a number. A cube root of 8 is 2, a cube root of 27 is 3, a cube root of 64 is 4, a cube root of 125 is 5. So I have to get bigger and bigger and bigger to get an answer that's bigger. So I'm going way, way bigger on the independent variable to get a bigger value on the dependent variable, but they always do get bigger. So as the bottom goes to infinity, dividing by infinity becomes 0. So this bit right here goes to 0. When it's infinity, in the same way that 1 over x went to 0, or 1 over x squared went to 0. So this is 0 plus 3, which is 3. Again, a surprisingly small answer for an infinitely wide amount of area. Maybe you're curious what that function looks like. So let's pull up our calculator. That was 1 divided by the cube root. I got to go into here to find that. There's my cube root. If you need any other 4th, 5th, 6th roots, whatever, that's this option. You would type the index, then that option. And then that was the cube root of x to the 4th. Look at how similar this kind of looks in the same window as that, that 1 over x before. It kind of starts pretty high up over here, but it flattens out quickly and quickly and quickly. Now, maybe it's flattening out quick enough to have a finite area, maybe not. Well, we showed that it was. The calculation was sound. Let's do that integral test and just see what happens from 1 to 10 and 1 to 50. I won't write them down this time. So lower limit of 1, enter. Upper limit of 10, enter. So from 1 to 10, this area is 1.6. Let's just go with 1.6. If I went from 1 to 50, though, so 1.6 versus it's taking a little longer because it's a complicated function. 2.2, 1.6 versus 2.2. So that's a gap of 0.6. That doesn't give, a gap of 0.6, you might say, well, hold on. When it was a gap of like 0.1, that was okay. When it was a gap of 1.6, that was too much. This is 0.6. I don't know. I mean, it is completely arbitrary. Some people might say, well, that makes me think, since it went from 1.6 to 2.2, with an increase of 0.6 in area, maybe that's going to converge, maybe it's diverged. Maybe that's not enough to tell. And that's why I'm doing this. I don't know that that's enough to tell just by looking at the numerical analysis side of things. But again, when you do the calculus, when you do the formulas, it does turn out that this area is 3. So if I really wanted to take like 15 minutes, I could make this thing as like 1,000 wide and just let it crunch and crunch and crunch, and it would still be less than 3. So if going from 1 to 10, the area was 1.6. Going from 1 to 50, the area was 2.2. Going from 1 to infinite, it's 3. So it's got another 0.8 to pick up from 50 to 1,000,000. And again, I could, on my own time, do that, but this function, you saw how long it took to crunch up to 50. Imagine this thing trying to do those rectangles or whatever in its own brain going up to 1,000. It would take like 10 minutes, but what you might want to do is download a TI-83 if you don't own one. Make the window from 1 to 1,000 and do what I just did, what I talked about. And I bet that area would probably be like 2.6, 2.7. I mean, that's just a guess. All right, now let's do D, the one we started writing earlier. The integral from, and let's just change the lower limit, no particular reason besides just to have it different. From 4 to infinity of 1 over the square root of x dx. Now your first instinct is probably going to be, after seeing that last problem, oh, this is going to be a finite area. It's going to have an answer. Let's execute and see what happens though. And you might think that because, oh, well, this last one had a radical in the bottom, so all radicals in the bottom are probably okay. Well, let's compare A and B. We saw an x in the bottom, you saw x squared in the bottom work, and you might think, oh, well, that means they're all okay if an x is in the bottom. Nope, this one is not okay. These radicals are the same thing as exponents, it's just fractional exponents, like a 4/3 instead of a 1 or a 2. So let's do all that changing. We know we got to do a limit as b goes to infinity. From 4 to b, and that's going to be 1 over x to the 1/2 dx, which is the limit as b goes to infinity. Integral from 4 to b, x to the negative 1/2. Then we can integrate it. Leave the limit. You got to leave that limit for a long time. Add 1 and divide by the same value. So what's negative 1/2 plus 1? Negative 1/2 plus 1 is negative 1/2 plus 2 over 2, which is positive 1 over 2. Interesting. So this is x to the positive 1/2 divided by a positive 1/2. No plus c needed, no dx needed. Evaluated from 4 to b. Dividing by a half is the same as multiplying by 2. We just made that argument in the last example. So that's 2 over 1 times x to the 1/2. Evaluated from 4 to b, which is the limit. As b goes to infinity, that looks like a 2. Of 2 times the square root of x, evaluated from 4 to b. Now we can plug in the b and the 4. So the limit as b goes to infinity. 2 square root of b, that's the upper limit being plugged in, minus, that's part of the formula, plug in the lower limit, 2 square root of 4. Some people like to put all this in parentheses to denote the limit is talking about all of it, not just the first bit. That's up to you. It's not technically necessary, though. Square root of 4 is 2, and I'm just going to say that's 2 times 2, which is 4. So that's the limit, as b goes to infinity. 2 square root of b minus 4. Again, the square root of 4 was a 2, then 2 times the 2 in the front gave us that 4. Now that there's no more crunching to do, this is where we want to think about plugging in an infinity. Think about what happens as this goes to infinity. As b goes to infinity, what happens to the square root? Well, if you take the square root of 1,000,000, you still get a big number. If you take the square root of 1,000,000,000,000, you'll get a bigger number. If you take the square root of 10 quintillion quintillions, you'll get a bigger number. So this square root of b goes to infinity. Now, if it was in the bottom, that would be okay because 1 divided by infinity goes to 0. But this is in the top. So the square root of b, again, would go to 0 if it had been in the, let me start that over. The square root of b would go to infinity, leading to 1 over square root of b to go to 0. And in the last example, we had a cube root in the bottom. So that cube root in the bottom made the whole thing go to 0. Again, when the radical's in the bottom, if that goes to infinity, you're dividing by infinity, so the whole thing goes to 0. This radical is in the top. When your radical's in the top, you're not dividing by infinity. This thing is going to infinity. This does not exist. There is a major difference in C versus D, just like there's a major difference in A versus B, albeit at a separate time. When your variables are in bottoms with positive exponents or radicals, because they're the same thing, the limit ultimately goes to 0. When your radical or whatever positive exponent's in the top, that limit will not exist because it diverges, it goes to infinity, all the different ways of saying it. It's just interesting because the cube root of x to the 4th versus the square root of x being in the bottom and that other thing being in the bottom, they don't look that different in terms of graphs. So let's go back to more of a standard zoom. Here is your 1 over cube root of x to the 4th. Here is your 1 divided by the square root of x, the one that it's about to draw. See how it does that same kind of tapering off? It's not as steep in the beginning here, and it's tough to see, so let's zoom in. Let's make our window. Let's go x. We don't care about the negatives for this stuff, so let's go from 0 to 10, and let's put the y scale from like 0 to 3 or 4. So there's the 1 over the cube root of x to the 4th. It's drawing slowly. And now here comes the 1 over square root of x. See, look, it's the same kind of happening when we compared 1 over x squared versus 1 over x. They have a greater rate of descent in the beginning, but then a much slower rate of descent after you hit x equals 1. That's their crossing point. So the 1 over 1 over third root of x to the 4th, it gets close and close to 0 quick enough that all of these little rectangles, those infinity rectangles going to infinity, are not really going to matter much. This one does not approach that axis quick enough. It's all about how quick the function closes in on that x-axis, and this is not enough. And it's just so funny because there's not a lot of width here. That's not a lot of room, but it makes all the world of a difference. So what's the reason for this? Why did it happen? Why did the one thing diverge versus the other converging? It's because after we integrated with the 1 over cube root of the x to the fourth, that x term ended up being in the bottom. No matter what the positive exponent was, it was in the bottom, so that's going to go to 0 when you take the infinite limit. But with this one, because that exponent in the bottom was smaller, when you added 1 to it, it was actually enough to bring it up to a positive exponent instead of the negative exponent, so we never tossed the x back in the bottom, it stayed in the top. And plugging in infinity into anything in a top is infinity. All right, so I love those first 4 examples. A versus B, great comparisons. C versus D, great comparisons. But we need to also see, what about these negative limits, negative infinite limits? Maybe we're going from negative infinity to 0, or negative infinity to 1, or negative infinity to negative 12, something like that. Or maybe even what if we have a limit from negative infinity to positive infinity? So we can also do improper integrals involving negative infinity. So let's go ahead and get all the little notation out of the way. There's not going to be anything crazy here. If you wanted to do the integral from negative infinity up to some number, and again, we typically let b represent an upper limit of some function, f of x dx, you'd have to make this the limit. And we like to use a for the lower limit. The limit is a goes to negative infinity, integrating from a to b, f of x dx. So again, the b is a number that was probably given to you already. I say probably, I mean definitely for this format. But we can also do this. The integral across the entire x-axis, the integral across the entire real number system, negative infinity to infinity, f of x dx. So the way you have to do this is you actually have to split it up into 2 cases, these 2 cases being what we just saw. You have to go the limit as a goes to negative infinity, integral a up to some random value. I don't really want to say c, so let me just say some number, because we've been using c to represent a constant of integration. And you could say we'll just use d, and yeah, that would be fine. But let me just say, go from a to a number, so from negative infinity up to a certain point, and then your regular old function. But then you also have to do plus the limit as b goes to infinity, and then integrate from the same number you stopped at previously up to b, f of x dx. This is the same idea that we've seen dealing with an area between 2 curves where they cross. Now, these don't have to cross. Sometimes they do. In fact, most of the functions that have convergent infinitely wide areas, you end up having to split this because there's an asymptote somewhere in the middle. It's usually 0. So first of all, you would probably need to split this up into 2 limits because of that, because there'd be a vertical asymptote somewhere. Second of all, you have to set this up into 2 integrals because of the unique limit situation of which I have an error on. This a is not supposed to be infinity. It was supposed to be negative infinity. I said it, I just didn't write it, because the lower limit is negative infinity. So the limit as a goes to negative infinity, so essentially this is going from negative infinity up to, say, it's usually 0. 0 is usually where we split this, usually. And admittedly, I'm not going to test you on that, so I'm not going to do any in the notes. So go from A to 0 and then 0 to B. If the vertical asymptote was somewhere else, you'd go wherever the vertical asymptote was. Say, let's say the vertical asymptote was at 1, then you'd go from A to 1 and then from 1 to B, where A and B represent the negative and positive infinity respectively. But we will do an example of this first case. So example 2. Evaluate the improper integral, same instructions as before. So let's go from negative infinity up to 0. And let's do e to the 3x dx. Now, the first thing some people think when they look at this is they go, it's divergent, it goes to infinity, does not exist. Because they see e to the 3x, and they look all the way back here, think all the way back here when we were doing the 5 cases we see the most, and oh, the limit as x goes to infinity of e to the ax does not exist. You have to be very, very, very careful about that. Every single one of these reminders was a positive infinite limit. There are a couple that are different when going to negative infinity. These two are unaffected. These two are the same for negative infinity. They are unaffected. So again, you might want to write this down. I'm going to erase it after a second. These two limits, if you are going to negative infinity, are the same. The first one still goes to 0. The second one is still going to go to infinity. It's actually negative infinity though, but that still just means it doesn't exist. These two are the same if you go to negative infinity as they are for positive infinity. These are different. First of all, the natural log is not defined for non-positive numbers. So there is no negative infinite limit for a natural log of x. There isn't even one at 0. So that one is different. These two actually flip-flop because of the negative in the exponent. So if you plugged a negative infinity here, those two negatives would cancel out, and now you've got a positive exponent. So now it would go to infinity. If you plug in negative infinity here, there's now a negative in the exponent, which means this thing goes to 0. So I'm going to write that note down. I'm just not writing it up here. So again, if you're thinking about a limit as x goes to negative infinity, it doesn't exist for the natural log because you can't even go past 0 in terms of left. These two things are the same. These two flip-flop. So first, note. The above limits are a little different negative infinity. The polynomial, that's ugly. I'm just going to have to. There we go. The polynomials do not change. The natural log will d and e, and the exponentials swap, as just explained. All right, so let's get to the work. Equals. I see an infinity, so I got to introduce a limit. As not b, a. I can use b, but I want to be more appropriate because a goes to negative infinity, and I won't forget my negative this time. E to the 3x dx. So this will be the limit as a goes to a negative infinity. Well, this is a nice simple integrand. We have a rule for that. It's e to the 3x divided by 3. There's no plus c needed because we're evaluating between, oh, I forgot my integral symbol. G's from a to 0. So we're evaluating from a to 0. I got so focused on the negative part of the infinity, I forgot my integral symbol, but we got it in the end. Okay. So we're going to plug in the 0. Leave the limit. Limit a goes to negative infinity. E to the 3 times 0. Then we're subtracting off the lower limit. And now this will be e to the 3a. And then both of these are also divided by the 3. Don't forget that. I thought about writing it all over just one single 3, but I changed my mind. Let's keep it split. So the first one was plugging in the 0. This was plugging in the a, which is arguably negative infinity. Well, 3 times 0 is 0, so that's just e to the 0. And remember, e to the 0 is equal to 1. So this is the limit as a goes to negative infinity of 1/3 minus e to the 3a over 3. Now we got to think about what happens as this goes to negative infinity. And again, exponential terms, if this was going to positive infinity, this thing would diverge. If this was going to positive infinity, this is going to be like e to the 10 billion, which is so large of a number I can't even think about it. But we're plugging in negative numbers. So this is like e to the negative 10,000, e to the negative 20,000, e to the negative 30,000. And when you have a negative exponent, you flip it. So now you're dividing by a really big number, which makes it really, really small. This is 1/3 minus 0. The limit as a goes to negative infinity of e to a positive term is actually 0. Because e to the negative infinity will go to 0. 1/3 minus 0 is 1/3. There we are. If that confuses you, what you can do is just swap the sign of the a. Just take, instead of having the negative here, just give it with your a. So some students do this. They go limit as a goes to negative infinity of 1/3 minus e to the 3a over 3. We do the same thing as the limit as a goes to positive infinity, but that switches the sign of the a, which switches the sign of the exponent. So that would be 1/3 minus e to the negative 3a over 3. If you want to remove the negative from your infinity, you have to throw in a negative with your variable. It's cool that that works. Whether you like to do that or not is up to you. I'm just giving you options, because then you don't have to memorize the fact that the negative infinite limits are different for some functions and not for others. And it all has to do with their graphs. Let's just go back and look at the standard zoom so I can see the left and right sides again. And I also don't want to see both of these functions. Well, I guess it's fine. Here's the 1/x². Look at this. On the left side, it flattens out to 0. On the right side, it flattens out to 0. Then here should be the 1/square root of x. I said 1/x², I think. That was 1 over the cube root of x to the 4th originally. It flattened out to 0 on the left, it flattened out to 0 on the right. The 1/square root of x is doing the same thing, even though you can't see it. If you have 1/x², or 1/x to any power, any positive power. Look at this, on the left and right side, they both flatten out in the same manner. It flattens out from below on the left and above on the right, but it's still flattening out to a height of 0. That's why those 1/x to the n's have the same conditions whether you're going to negative infinity or positive infinity. But when you have your exponential terms, your e to the x's, they do different things on the left side and right side. On the left side, it decays, it flattens out to 0, but on the right side, it grows. E to the negative x, it does the exact opposite thing. See? Grows on the left, flattens out on the right. So exponentials have different limits left or right sided. When we do the natural log of x, it doesn't even have any graph on the left side. You can't go past 0, you can't even use 0. So there is no limit to negative infinity because the function doesn't even exist anywhere close to it. But on the right side, it goes up very slowly, but it does go up forever and ever to positive infinity. So you have to still maintain a basic understanding of these three core types of functions. Polynomial types, which also gets to include radicals, thankfully, your exponentials, and your natural logs.
And that's actually going to be it for us for the evening. Since you've got your test on the horizon, and the next section is a little longer, and I just didn't want to really get into. Actually, I'm sorry. The next section is kind of short, so it means that you were going to have 3 homeworks due in the same week. I was thinking of the wrong thing. I didn't want to do that to you, so we're just going to go ahead and cut it there. So please make sure you get those 2 homeworks done, as well as the stuff from chapter 4 if you have the previous stuff from chapter 4 if you haven't already. Make sure you take that test over the next 3 days. Make sure you've got a webcam enabled when you do that. Make sure you understand how to use the lockdown browser. Should be pretty simple, I hope. You're just going through my math lab per usual with a couple extra steps. Make sure you've got 2 hours available to take it. And we'll be back next week. I think next week might actually be our last lecture. I think I'm going to be able to finish the material that I need to finish with us, and then we can just do the final the week after that. But don't count your chickens before they hatch yet. I will let you know next class. So as always, if you have any questions, please shoot me an email. Besides that, have a good week, study hard, work hard, get those good grades. And we will see you next Monday evening. Take care, everybody.